So this is the second video module on thinking algorithmically, and in this module we're going to look at a particular problem that we'd like to develop a set of algorithms for, and the problem we're looking at is called an assignment problem. Essentially what we have, if you see our matrix here, is we have 4 tasks, A, B, C, and D, and 4 people, Tom, Jim, Jane, and Kate, and the problem at hand is to assign tasks to people. And to facilitate our algorithm design, we're going to define something called the cost matrix. Actually, we're just going to define the notation for the cost matrix. In particular, we're going to let Cij be, be the time for person I to perform task J. So essentially we just took our matrix that we have here and gave it the Cij form. So in other words, if I look and say, how long does it take, or what's the notation for Jim to do task C, we can see that I would be equal to 2, J would be equal to 3, and so we would have C2, 3, which would give us a value of 1. So we're just taking this cost matrix and giving it a more formal notation that we can use in our algorithm. Okay, so suppose at this point I have no other information about my assignment. I know that the task at hand is to assign, to assign the tasks to people. So one algorithm for doing this would be as follows. Let's just say for each task J, assign J to a random person. For each task J, assign J, that task, to a random person. And so you can see that this would definitely be an algorithm. We solved the problem that we have, which is, again, just to assign tasks to people. Of course, we're not sure that this, is what we really want, because for this solution, we could easily end up with a case where one person gets assigned all tasks, or 2 people get 2 tasks each, or something like that. So it might be that we want to further constrain our solution. So we might want to add some constraints before we do our algorithm. And some potential constraints might be things like each person gets exactly 1 task. Each person gets exactly 1 task. Of course, this constraint implies that we have the same number of tasks and people. In this case, we do. We might have other constraints too. We don't necessarily have to have this constraint. We might say each person gets at most 2 tasks. Each person gets at most 2 tasks. And if we didn't have this constraint, or if we didn't have this situation where we have equal number of tasks and people, we have other options too. Like we might say each person gets at least 1 task, or at least 2 tasks, or something like that. The basic idea is when we add constraints to our basic problem, that's going to influence the algorithm that we develop. So for our initial attempt, or initial work, let's just assume that we've adhered to constraint 1. That what we're going to do from a constraint standpoint is we're going to ensure that each person gets exactly 1 task. So an algorithm to do this would be as follows. For each task J, let me just start that over, hopefully read that. Let I be a random person who doesn't have a task. Who doesn't have a task. And then assign task J to person I. So our algorithm is we're going to cycle through each task, and we're just going to pick a random person who doesn't have a task. Now clearly the difference between our previous algorithm and this one is this who doesn't have a task notion. And so one fundamental component of algorithm design is that we don't want to get caught up in how we're going to do this. In particular, if you're new to a programming language like Python, you might worry about how am I going to do this? What does this mean, from a coding standpoint? And what we really want to do is try not to think about implementation details at all. We want to banish those implementation thoughts so that you can focus on what is the algorithm and what's the process that we're going to follow. We will definitely have to come back to that from an implementation standpoint when we're going to actually implement our algorithm, but now's not the time to do that. During the algorithm design, you want to focus exclusively on the algorithm itself and leave the implementation details for the next phase where we're actually implementing the code. Okay, so our new algorithm gives us a solution, and it adheres to our constraint of exactly one task to each person. And it works, but we might want to think about something else. We might want to think about making good assignments. So let's think about the notion of good assignments. What we're really after here is something called an objective. And there are several different objectives we can consider for this problem. Let's think about one objective might be minimize the total task time. Minimize the total task time. So this would be something like, I want to minimize the work done, or minimize the total time expended by all people, or something like that. I might also want something like minimize the difference between assignments. Minimize the difference between task assignments. So something, fairness. It's not fair if you have a short task and I have a long task, or vice versa. So I might have an objective that says I want to balance the workload or something. And there are other objectives that we could have for our problem. We're just going to pick this first one. Turns out this is a fairly straightforward objective to have. And so now what we're going to do is we're going to modify our algorithm, or actually create a different algorithm where the objective is to minimize the total task time, and we're constraining the solution so that each person gets exactly one task. So the problem that we've just defined is something called the linear assignment problem, or LAP for linear assignment problem. Turns out this linear assignment problem is fairly easy to solve, but that's not our interest. Our interest at this point is not solving this problem optimally. Our interest is in designing an algorithm, or talking about the general notion of algorithm design, and this just happens to be a convenient problem to discuss. So here's the first algorithm we're going to look at to solve this particular problem. We're going to call this STT for shortest task time. And we're going to name it too, because we're going to come back and use the name here a little bit. So we're going to let Cij, as we said before, be the time for person I to perform task J, just as we said before. We're going to keep track of the total cost, so we're going to set the initial cost equal to 0, and then we're going to loop through the people. So for each person I, we're going to find the minimum cost unassigned task. And we're going to call that J. Then we will assign task J to person I. Then we can update our cost, so our overall cost, that's not a good S there, let's try that one more time. Cost equal cost plus Cij. And that's algorithm STT. So we're going to define our cost matrix, which we'd actually already done. Then we're going to initialize our cost, initialize our accumulator, our cost accumulator, and then we'll simply loop through each person I, and then for each one we'll find the minimum cost unassigned task. So again, let me reiterate, when we think about this line here where we're trying to find the minimum cost unassigned task, this implies that we will track the assignment and that we'll then maintain a list of unassigned tasks and somehow be able to find the minimum of that. And what you absolutely don't want to do is focus on how am I going to do this in Python or whatever language you're doing, because we understand intrinsically what this means, and when it comes to the implementation stage, we'll figure out how to do it. But at this point in the algorithm design stage, you don't want to bias your thinking by focusing only on what you already know how to implement. So again, clear separation between the algorithm design and the actual code implementation. Okay, so now that we have our algorithm design, let's see how this might work. So let me grab this guy. We still have our cost matrix there. And how would the algorithm work? Basically, we would say, okay, our cost is equal to 0. Here we are at this first line. And then we'll just cycle through the people. And we'll just start at the top and go to the bottom. And step 1 basically says, for each person, and our first person is Tom, find the minimum cost unassigned task. So all the tasks are unassigned. So clearly this is task 5. Now we're going to assign task J, task D, or task 4, I should say, not 5, and assign it to Tom. And basically that means this task is done. It has already been assigned. So when we come back and look for unassigned tasks, it won't be included in the list. Now cost is equal to cost ij, so now my cost is equal to 5. So we loop back up. Our second person is Jim. We have 3 unassigned tasks, and so clearly Jim is going to be assigned task C, and our cost is going to go to 6. When we go to Jane, Jane's minimum cost unassigned task is A, and so we now have, what is this, 102? And then finally for Kate, there's only 1 unassigned task, so Kate gets it, and so our total cost is 152, and our assignment is Tom gets D, Jim gets C, Jane gets, what does Jane get? A, and Kate gets B. And so our solution to our algorithm is 2 things. Our solution is the actual task assignment combined with the cost of that assignment. So now the question is, what is it that we assumed when we solved this problem? In other words, we did our algorithm. What assumption, oops, scrolled too much. What assumption did we make? What assumption did we make when we solved this problem using our algorithm? Remember, the constraint was given to us and the objective was given to us. The assumption we made is the sequence at which we visited people. So it's the people sequence. And if we use the row numbers, we basically assume that we were going to go from the top to the bottom. 1, 2, 3, 4. Okay, and so the question would be, well, what would happen if we did a different sequence? So for example, suppose that, let me grab this guy again. Suppose that we did the sequence from the bottom to the top. So we did sequence 4, 3, 2, 1, and everything else was the same. Well, we would start here with Kate. Kate would get task D, then Jane would get task C, then Jim would get task B, and Tom would get task A, and our cost would be 2 plus 18 plus 12 plus 12, 20, 32 equals 44. So based on our objective of minimizing total assignment costs, clearly the sequence 4, 3, 2, 1 provides a better solution than the sequence 1, 2, 3, 4. So what we're going to do for our next algorithm, or our next iteration, we're going to call this algorithm STT1, is pass the sequence as a parameter. So we're going to notate it this way. So we are passing the sequence as a parameter, so that we can change, so that we can give it the sequence that we want. And so the full algorithm would be very similar. I'm not going to recopy the definition of CIJ. You guys can get that. And so we're going to just say cost equals 0. So we initialize our cost. And this time we're going to use the sequence that's provided to us. So it's just going to be for each for each I in sequence, because remember, sequence is the sequence that we're going to visit the people. The sequence that we're going to visit the people in the matrix, we are going to just do what we did before. Find the min cost unassigned task. Call this J. Then assign J to I, and cost equal cost plus Cij. And so algorithm STT1 will allow us to specify the sequence that we want to visit. Okay, so now we're going to do the next one. Algorithm STT2. For STT2, we're just going to formalize the process that we did when we investigated two sequences. So it would be something like this. Let's say that our V1, or our solution 1, is equal to STT1 using the sequence 1, 2, 3, 4. And so what we're saying here is I'm going to execute algorithm STT1, and I'm going to use the sequence 1, 2, 3, 4. That's what we mean when we talk about passing the parameter. So I'm going to pass the sequence as a parameter, and then what comes back is the solution. So it's going to give me the solution to the assignment along with the assignment. So we're then going to say V2 is equal to STT1 using our backwards sequence, 4, 3, 2, 1. And now to choose the better of the two, we're just going to say if V2 is less than V1, then we're going to use the sequence 4, 3, 2, 1, else use 1, 2, 3, 4, like that. So one quick note here in terms of the return values. You might have noticed that when we did algorithm STT1, we didn't specify anywhere that the cost and the assignment gets returned, but in algorithm STT2, we actually assume that that happens. So when we talk about V1, for example, and V2, we used V1 and V2 here to represent the cost, even though we didn't explicitly return that. And so that, when we implement this in code, then clearly we're going to have to define that. We'll have to define a data structure that stores the value and appropriately returns it and so on. But as I said, that's really an implementation detail, and it's fairly clear from the context exactly what we're trying to achieve. And so again, part of this algorithm design is this trade-off between specificity and saying this is exactly how I want it to work in terms of data structures and everything, and just getting the concept across. And what you want to focus on early is just the concept, so you don't get bogged down by all of those details. So if we look at algorithm STT2, of course a natural question comes up is, well, we only chose two possible sequences. There probably are better sequences. There quite certainly are possibly better sequences. So what if we wanted to test all sequences? All sequences of people. Sequences of people. So we're going to do the same basic process that we did in STT2, but we want to go through all sequences. Well, when we do this, we need to introduce the notion of an incumbent solution. Incumbent solution. And so what we're going to do is we're going to keep an incumbent solution. We're going to then sequentially see if we can improve on that incumbent solution. So our final algorithm STT3, is going to be as follows. Our incumbent solution consists of two things: min cost, which we are going to set to big M. So this is big M. If you're not familiar with big M, it's just a really big number. Then we're going to have our solution, which I'm just going to call SOL, is equal to null. And so min cost will be the minimum cost, or the cost of our incumbent solution, if you want to think of it that way. And SOL will be our incumbent solution. And so when we start the process, we don't have a solution. So what we're going to do here is we're just going to say for every. Well, let's just do each. For each possible sequence of people, which we will call SEQ, cost is equal to STT1 sequence. So we're going to pick a sequence. We're going to pick all the sequences actually, but we're going to use them sequentially. We're going to execute STT1. Recall STT1 then just solves it. And if the cost, we're going to compute the cost STT1. Now we need to say, is this solution better than our best incumbent solution? So we're going to say if cost is less than min cost, in other words, if the cost that we just computed given the sequence is less than our minimum incumbent cost, then we want to store this solution because this current solution becomes our best incumbent solution. So now we want to say min cost equals cost and solution equals sequence. Oops, that's a terrible looking sequence. SEQ. And so our algorithm STT3 basically says I'm going to store an incumbent solution which has two components, a cost and the actual sequence, and then I'm going to iterate through all possible sequences, checking each one. And if a particular solution is better than the best incumbent, it then becomes the best incumbent. Now, I know what you're thinking. You're thinking, how in the world am I going to get all possible sequences of people? And again, this is something that we don't want to think about while we're doing algorithm design. Clearly, we will have to solve that problem. And it might be that when we're solving that problem, we come back and change our basic algorithm. But at this point, we're going to view that as an implementation detail, and we're going to push that off to the side, think about our algorithm, and then we'll come back and address that next phase for implementation. So the question now becomes, when I look at algorithm, is it good? Does the algorithm work? Okay, and so this is really a question for another day, a totally new module or totally different context here, but I will just tell you that this does not give the optimal solution, so it doesn't give the guaranteed best solution. Again, that's a topic for another day. What it does do is, what we have done in this module is we've systematically developed what is potentially a good solution or a good mechanism to find a solution to this particular problem. And of course, the next step, if we wanted to test this, would be to do the second part, which is the actual coding step. So I would then be converting my algorithm into executing code.